Hello, everyone. Uh, Good afternoon. And I thank the organizers and especially Rajaram for inviting me to give this talk today. And I'm going to talk about relational representations and reinforcement learning. This is a little wide-ranging talk in the sense that I'm going to talk about two different pieces of work that we have been working on recently. But before that, I'll also try to motivate why do we need this relational representation setting. So before I get into the meat of the talk, I just want to acknowledge our team. And this was joint work done with Professor Sriram Natarajan at UT Dallas, and Prasad Thadekpalli at Oregon State University, along with Harsha Kokal, who's a PhD student working with Sriram, and Arjun and Ashutosh, who are master students working with me and jointly advised by Sriram as well. So, but everybody talks about reinforcement learning, and in fact, reinforcement learning success is not even new. Right. So if you go back to the Samuel's checker playing program, the learning program back in the 50s, right, that was a form of reinforcement learning. In fact, it used reinforcement learning with symbolic representations, not necessarily relational, but symbolic representations. One of the earliest stories of success of RL with the function approximator, even though people didn't view it as such back then. Right. And then, of course, more recently, you have had much bigger news stories such as AlphaGo, which was the first computer program to defeat a professional human Go player, right? And then it's followed by AlphaZero, which used even lesser data than AlphaGo did from a human. And it just trained from scratch by playing against itself. And then now the next generation of this is MuZero, which is even more powerful than AlphaZero. And so it's one of the biggest advantages touted for this is that there are no human features that were required for learning AlphaZero. It just could learn from raw positions on the board. Right? And then you have other things like StarCraft, which is a much more complex domain. But again, really not much of hand-coded representations or anything. It just learned from looking at more stylized representations. Right? Then there is more non-game playing success story, which is in AlphaFold, which was a protein folding algorithm, right? So it solved the quote unquote solved, right? The protein folding problem very recently, and the community was really surprised. Like they didn't expect the problem to be solved so quickly at this point, right? So and then we have all of these success stories, and the people have now started believing that reinforcement learning works. In fact, I'm very happy that I could give a talk right now to you, just by starting with the success stories of RL and not telling you what reinforcement learning is. And back when I started working in RL, I really needed to tell everybody what is reinforcement learning, and then get into more nitty-gritty details of it. But right now, I don't have to tell you that because everyone knows what reinforcement learning is. It's significant excitement in the community, as you can see by the exponential growth of papers. But a question I really ask, hey, come on, does RL really work? Because there are many fundamental questions that you still have to address, right? So let's take one of those. Right? Looking, as with any machine learning algorithm, right? Reinforcement learning is still learning associations from data, right? And this leaves the models very fragile. So here is an example. So there's an amazing thing, right? So it's now there's a blue agent and red agent are playing soccer, and you can see that the blue agent has learned to, reasonably score goals, right? The red agent is learning to reasonably defend it, right? But then this is because both the agents are trying to play the reasonable strategy. But let's say I have an adversarial goalie, and you can see what the goalie does. So instead of actually trying to defend the goal, the goalie just lies down on the ground and starts crying, and this completely confuses the blue agent, right? It's not even trying to reach to the ball. It's like acting like a drunken fellow because it's never seen these kinds of behavior, and then so it doesn't learn, right? It just completely degenerates, right? So the problem is because we are learning associations from data, we really don't have a model of how this whole process works, right? So what is the fix? So I mean, there are many things that we could actually try and work on here, and I'm going to argue that we really need to go back and look at more classical AI, look at logic, reasoning, and planning. Look at more semantically informed representations, look at symbolic representations, relational learning, and look at spatial and temporal abstractions. and perhaps look at causal modeling, go beyond that, right? Look at world models and look at dynamical models of the world and use them to make predictions as how the world will evolve and so on and so forth. Make use of everything that you know about the problem and don't say that, I'm going to solve everything from scratch, right? And so in this talk, I'm going to talk to you more about racial representations in RL. I know I changed the title slightly. The reason I'm partial towards looking at this direction because I'm really interested in building systems where a human can work with reinforcement learning agent more comfortably, right? So it's more amenable to human in the loop learning because relational representations are in some sense more interpretable, and it's easier, to specify domain knowledge and even instructions that I would like to pass on to the agent when I'm working in a more abstract symbolic space, right? Where I can think in terms of objects and relations between them. Right? And it also allows us to integrate with more classical logical reasoning work, that probabilistic logical reasoning work that people have done, and as well as planning frameworks, right? Where we really would like to do deliberative plannings at some point in the architecture and more reactive learning, right? So so you can basically achieve a really powerful generalization through this process known as lifted relational inference of relational learning. It's where you don't really work in the base space, but work in some kind of a generalized object space. Right? So that is really a powerful generalization mechanism. Right? So what I'm going to talk about to the rest of the talk is basically two challenges. Right? So one, talking about doing online learning with this kind of statistical relational representations. And then also talking about a framework where I can integrate domain knowledge, right, in terms of what I know about the structure of the world and the structure of the solutions, right, and learn what I don't know, right. So coming up with a unified framework where I can easily integrate prior domain knowledge and learning. Right, so these are the two things I'm going to talk about. I'm going to keep the talk at a slightly high level because I know that this is not necessarily a reinforcement learning audience. So I hope that I can interest you enough to go look at some of these papers later. Right. So the first thing I'm going to talk about is online learning. So the typical relational learning frameworks operate on batch data, right? There are very few approaches that work on online learning, typically because the inferencing process that we use is pretty expensive, and so you really don't want to get into online setting. And people haven't really looked at the exploitation trade-off that usually comes with this kind of online setting. Right, but this exploitation trade-off is very crucial for reinforcement learning, and so what we have worked on is something called relational boosted bandits. You'll see why in a bit, and this is accepted at IIII and will be presented at the conference shortly, right? And so the idea here is we are going to propose a exploitation framework, right, for online learning, but that uses statistical relational representations underlying. So before I go on further, I just want to make sure that we are all on the same page when I say relational representations, right? So essentially, we are looking at heterogeneous data. And so the traditional machine learning approaches tend to flatten out this kind of heterogeneous information, like, so they kind of ignore entities and relationship and then try to make a single vector out of it, right? And so what statistical relational learning does is tries to keep the relational structure intact, right? And at the same time also accommodate any kind of uncertainty that you have about the properties of the entities and the relationship between the entities and so on and so forth. And since you learn at the level of entities and relations, so quite often the result of the learning task is more understandable and interpretable than a flat vectorized representation. So here are some examples. So you could think of these as various entities that exist. So the IMDb data set has movies, actors, studios, producers, and directors, and relationship between them. And same thing with the Cora data set. And you also have these entities by themselves have features, right? So paper could have a collection of keywords and publishers and authors could have areas that they publish in. right? And similarly, actors could have genres they act in, and so on and so forth. And movies could have like box office receipts. It could be a variety of different attributes that go along, or features that go along with each of these entities. So you have these entities, features of the entities, as well as relationship between entities. So this is what we talk about as relational data. And when we talk about statistical relational learning, we say that, okay, some of these I'm not sure, right? Some of these uh, relationships might be true or might not be true with some probability, and so we tend to accommodate that as well. And the problem setting we are looking at is the one of contextual bandits, right? So the bandit framework is in some sense a distillation of one of the key problems of reinforcement learning, and that of exploration versus exploitation trade-off, right? So I have these multiple actions that I could take. In this case, there are many articles that I could recommend, but I do not know which article would be liked by a person who is coming to my web page, let's say, right? So I really have to try different articles, like try recommending different articles and see how the user reacts to those articles, right? And then once I have a sense of how much the user likes different kinds of articles, then I can go ahead and start recommending a specific type of article to them, right? And of course, there's all this debate about whether the machine learning algorithm should over specialize or should they still stay general and all that. We are not getting into it, but this is a basic setting, right? And so the exploration part is, trying to figure out what your interests are, and the exploitation part is once you figure out what the interests are, then keep showing you more and more articles of that type, right? So that's the simple bandit setting, right? And the contextual bandit comes into play because we have a lot of information about both the users and the articles. So we have things like location, age, interests, past history, etc. And about the article, we could have length, publisher, author, topic, and so on and so forth. So you would like to actually take advantage of all of this information in order to learn richer policies, right? And therefore, instead of learning a personalization for each individual user, you could potentially generalize across multiple users and also generalize to articles that were previously unseen by looking at the context or the features of those articles. So that's basically the setting, right? And so in fact, many contextual bandit approaches actually model real-world user interactions, right? Whether it is ad selection or looking at news or movie recommendations, or sometimes clinical trials, and as a substitute for A/B testing, and so on and so forth, right? So what relational boosted bandit does is combines contextual bandits with statistical relational learning, wherein we basically, so if you remember, what we are interested in is figuring out how likely is an article to be clicked by a user, right? So that's what the click-through rate question is, right? So the representation of how likely an article is to be clicked on by a user, right, is through what is called the relational regression trees, right, which essentially uses statistical relational learning, but learn a decision tree. So the decision tree where the internal nodes are defined on predicates, right, and on first order logic formulae sometimes, right? And we combine this with gradient boosting to allow for incremental learning of the trees, right? So it basically simultaneously it learns both the structure of the tree as well as the parameters that you need for representing the regression function. So, and what we are regressing on in this case is one of the click-through rate. But what is challenging here is that it's not a standard regression problem, because we are in an online learning setting where we don't know the target a priori, right? So we really have to do the exploration and figure out, right? So people have looked at it in the past, but then kind of weakening the exploration component, right? And then assuming that there's already this batch setting that is available, and then they learn on that. So this is the first truly online approach to fitting a regression tree for the click-through rates, right? So here is an example of a relational regression tree. Like I said, I mean, so you have the predicates that are there, right? So here is we're looking at whether a person A was advised by person B or not, and so you have questions like whether the A or B is a professor, have they shared, how many publications have they shared together, right? And how many publications or has one person produced, and so on and so forth. So you can actually, now you don't have the simple predicates. You can look at things like count and sum and min and max. You can look at more complex aggregate functions, and that lets you learn a very complex regression tree, right? And so the leaves here represent the regression value. And in this case, these are parameters that get plugged into a distribution function that essentially returns to you the probability that A is advised by B. Right? And so here is the setup for the relational boosted bandit. So that is a relational regression tree that kind of models the expected click-through rate, right? So the relational regression tree is kind of representing the expected predicted reward, or in this case, the click-through rate, right? And based on that, and based on the user context, the learning agent is going to pick a set of articles or an article to suggest to the user, right? And because I'm talking about the bandit setting, so I'm going to add exploration in the action selection. I'm not just greedily picking whatever the most likely article to be clicked. And then I suggest that to the user, and the user gives me a feedback, right, whether he likes the article or not, right? And then that is basically fed back to the learner, right? And in this case, what we do is we use the current state of the regression tree and make a few choices, accumulate a batch, right? And then go back and sample from that batch of data that we have accumulated, right? And one of the key innovations that we have introduced in the relational boosted bandit setting is what we call informed sampling, as opposed to randomly sampling it or picking the most erroneous predictions, right? Normally, in fitting this statistical relational learner, right, in the RRT GB framework, you would pick data points on which you currently are making the largest error, and it turns out that that tends to leads to overfitting, especially in this online learning setting, and therefore we had to come up with a better way of sampling data from the batch in order to update the regression tree. So that's essentially the overall flow of the relational boosted bandit approach. And here are some empirical results that we have. So you can look at the paper for more discussions. These are various data sets, and you can see that the blue line at the bottom here, that is a blue line that's just kind of, you can't make out the difference between the blue and the yellow. So the blue line at the bottom is the relational boosted bandit that includes exploration as well as the informed sampling. And the greedy RB2 is a variant that doesn't include the informed sampling part, right? And the batch RRTGB is just the relational regression tree with boosting, right? Just the standard one that looks like operating on offline data. And the epsilon greedy is where we have exploration for the action selection, but no sampling or anything. The update proceeds as it is, and you can see that it is important that we need all components of the learning, right, of the relational boosted bandit in order to get a better performance. You can think of this as some kind of an ablation study compared against batch RRTGB, which is the base algorithm, right? And the other nice thing that comes out of the relational boosted bandit framework is that you learn policies that are relational trees, right? So you can basically look at the policy, and here is a function that was learned for predicting whether A is a co-author of B, right? And you can see that this is pretty kind of reasonable. At least you can look at it and make sense out of it, right? It's not like a very complicated neural network, which is more like a black box. Right, so this is essentially the key contributions in relational boosted bandit, right? And the informed sampling algorithm that we actually have proposed is actually a parameter-free sampling algorithm. So it operates very quickly, and it's very suitable for online relational learning. But then the challenge here is we just use softmax exploration. That I'm pretty sure we can improve on the exploration strategies by looking at some of the power that the representation gives us. And I told you that I'm moving to this kind of relational learning because we want the human in the loop, right? And we still don't have a human in the loop system for online learning, and we would really like to move to that, right? And I have about 5 minutes left, and so let me see if how much of the second work that I can get through. And so here I'm talking about integrating prior domain knowledge in a unified framework with learning. And there have been several attempts at it, right? But what we really feel is that none of these truly leverage the power of state abstractions and hierarchy. Right? So there are hierarchical planner approaches which do some kind of learning, but they don't really look at the power of state abstractions. And I'll explain what we are looking at as we go along. So what we have proposed is what we call a relational planning and RL agent, which is called RepRel agent. The paper is currently under review, so I can't point you to a manuscript yet, right? So, but the whole motivation here is really right. So for a human level general intelligence, the ability to detect compositional structure of the domain and be able to abstract out hierarchies, right? So that I know when I can reuse problems, when I can compose problems together to solve a larger task, so on and so forth. And forming task-specific abstractions, right? So for when I'm looking at a task, I really want to pay attention to the features of that task, right? These are absolutely essential quantities for human level general intelligence, and kind of it's something I believe in, but I can also rely on other minds to support it, right? So we are going to look at the hierarchical planning framework, and so the hierarchical planning framework, you have predicates, you have operators, you have methods, and the methods come with preconditions and subtasks, right? And the operators also have preconditions, effects, and so on and so forth, right? So the planning problem is, okay, given the domain and the initial state at which the agent is starting, and given a task list, to figure out what are the various methods and operators that you have to decompose this task list into, so that you achieve all the tasks that you have set out. Right, that's a hierarchical planning setup that we are looking at. And the RepRel setting, you have the hierarchical planning domain, but some of the operators that you have to execute, right, are not known completely. So you know the preconditions and effects, but you really don't know how to achieve those. And so at the higher level, you do deliberative planning, but as you go down in the hierarchy, and you have to come to a point where you have to execute actions, right? You might have to learn the policies for the various operators. Right, so that's basically the setup here. I mean, the more details are there in the manuscript, and so the advantage is obviously have compositionality. But the biggest advantage that we have in RepRel is that we come up with a way that the planner, the higher level planner, can tell the reinforcement learner what is the task-specific abstraction the learner has to look at, right? So it can ignore all the other information. So for example, let's take a simple task here. So this is called the taxi domain. So I have a taxi, and then I have 4 locations that the taxi can go to. That's P1, P2, D1, D2. So I really want, so P1 is the passenger. So, and the passenger 1's destination is D1, and passenger 2's destination is D2. And my task would be transport P1 and P2, right? So basically that means take P1 to D1 and take P2 to D2. I can decompose this and say, okay, hey, transport P1 first, finish that, and then transport P2. And then I can say pick up P1 and drop P1, pick up P2 and drop P2. So this is all of these are specified in terms of operators in my planner, in the symbolic planner, and then we execute that. But then when I come to this actual actions like pick up P1, drop P1, right? And then I set it up as a reinforcement learning problem. And so one of the things you can look here is when I'm doing pick up P1, I really don't need to know where is P2, where does P2 want to go. In fact, I don't even need to know where P1 wants to go. And all of this can be specified basically by looking at the preconditions and effects that I have for the pick up P1, right? So, and then that gives me a much simpler problem for the reinforcement learning agent to solve, right? And I'm going to skip this, even though it's a very important part of whatever we did. And so there are these first order conditional influence statements, right, which says that if some condition holds, then X1 influences X2, but not otherwise, right? For us to figure out formally what are the features that are needed for providing an abstraction like this, right? So this is the full problem representation, and I want to give you this abstraction. For me to provide this abstraction, I needed to define dynamic first order conditional influence statements that not only tell you, okay, if this condition, then X1 influences X2, but it also tells you what is the time dependence between this influence, right? So I'm kind of being vague here because we're running out of time, but I'll give you pointers later. I will share it with organizers who can then pass on these pointers to you, right? So the one thing that we show in the paper is that if the MDP that I'm constructing for my RL agent to solve satisfies the dynamic Fauci statements, right, with some kind of fixed depth unrolling, right, and then I have a safe abstraction, right, and so it gives me fantastic generalization across objects, as we will see here, right. So here are some examples that we ran. So this is the office world. So you have an agent that needs to do multiple tasks in this office. So the agent is here, it has to fetch coffee, and it has to work in the office, and then go to the mail room, variety of things, right? So you start off by learning to deliver mail. So HRL is just hierarchical RL, TRL is taskable RL, which is a setting that is pretty close to what we are looking at, right? But so when we try to deliver mail, you can see that rep RL learns faster. Now I want to deliver coffee, right? So when it do rep RL plus transfer, that means if I take the agent that has already learned to deliver mail, I ask you to deliver coffee, and then so TRL plus transfer. So you can see that TRL is great at doing transfer because of the way it does the learning, but rep RL plus transfer also is doing pretty good in this environment, right? Even though it has not learned to deliver coffee before, it has learned to deliver only mail, but still it does very well. And then when I actually move on to a more complex problem where I had to deliver both mail and coffee, while I've been trained on only deliver mail, and you can see that rep RL almost is there, right? It basically is able to execute the policy almost immediately. And similarly, in the Minecraft domain, you can see that rep RL is amazing at transfer, even though it has never looked at the same problem of make stick before, right? The problem that it solved first was get wood and iron, and it's able to do that. So I can explain how this works in the taxi domain much easier. So you can look at this. So we start off by training the agent to drop only one person, just drop P1. But then for every run, right? So P1 could start at R and go to B, or start at G and go to Y, and so on and so forth, right? So every time I train the agent, even though it is dropping only one passenger, okay, it is trained only on trained on different locations. So when I go to drop P1 and P2, right? Now it's come to a situation where it has never seen two passengers before. But then the symbolic planner is able to accommodate for that. And the reinforcement learning agent, by virtue of the state abstraction that we saw earlier, right, now focuses only on P1 or P2 at a time. And since it knows how to pick up or drop one passenger, it has already learned all that policies when it learned to drop P1. So whether you are dropping P1 and P2 or dropping P1, P2 and P3, it doesn't matter. It's already learned the policies. And whatever is the generalization that is needed is done by the hierarchical planner. And because the planner is able to identify the right abstraction for the RL agent, we are able to do much more efficient generalization. And you can see the same thing here in a box world domain, where you have a set of boxes and which have keys that need to open them, right? And you can start off with very simple training where I have the key and I just have to open the lock. In this case, I just have to open the blue lock. But here I have to first get the red key and then go and open the red lock, right? And then you can see that rep RL plus transfer is doing really well. But here is even more amazing, right? Now I have multiple keys and multiple locks, and the rep RL plus transfer is literally is up there, right? It's not even learning much, right? Because it's able to transfer across these, even though I have many different objects, right? And that I have to work with because of the generalization that I have learned, right? So in the future, we have to look at how we can combine this with deep representations, or how I can elicit these dynamic Fauci statements in an incremental manner. Right now, we assume these deep Fauci statements are also given to you a priori. And also right now we assume that whenever I set out to make a plan, I'll always succeed. So how do we accommodate plan and learning failures? That's another direction that we have to look at. So summing up what I said earlier, so deep RL has revived excitement in the community, but we still have a long way to go before we have a completely acceptable solution. So thank you. And so if you have any questions, please feel free to write to me. You can also visit our website for more about our work.